The next two tests we'll look at are both going to be comparison tests. So we've got two of them, the direct comparison test or just the comparison test. These are interchangeable. The other one is specifically called the limit comparison test. So we start with the direct or just comparison test. So we have to have two different series, and we'll have our known series here. We know the behavior of this one, and this one is going to be from the problem. So if we are able to establish that we have a convergent series, first off we use a known convergent series, if we are able to establish that a sub k is always less than b sub k, then our series and our problem will converge. The idea is if b sub k has to be bound by something, then a sub k does too. On the other hand, if we have a series that we know diverges, and we know that a sub k is greater than that, then a sub k will diverge also. So b sub k will sort of act as a floor that's moving up and pushing a sub k up and making it so both diverge. So as it says here, we only need to really look at terms in the tail. We don't necessarily have to have for all terms these inequalities, but just for some after some positive integer n. So if we go ahead and look at some inequalities here that we can kind of establish. First off, we have the known p series where we have 1 over k squared, and we have 1 over k squared plus 10. Right, so I'll show us the idea. You can, in our eCampus page, you can go ahead and look at these if you want. We'll go ahead and look at the inequalities themselves. So the way that we'll establish this is we know that k squared is less than k squared plus 10. So we go ahead and divide by k squared and by k squared plus 10, and it essentially swaps around. It essentially swaps around these numerators into the denominators. So bigger denominator makes a smaller number, right? We know that. So from here, we know that 1 over k squared converges. So since 1 over k squared is a convergent p-series, and we have that 1 over k squared plus 10 is less than 1 over k squared, this series here converges. And we say by direct comparison test, DCT. All right. On the other hand, we look at another p series, 1 over root k. 1 over root k, the p there is 1/2. That means this guy has to diverge. And so we look at this guy here as our comparison. We see that the index is now 4 because we established the comparison starting with k equals 4. And we'll go ahead and do the same kind of thing. We know that k is less than, k minus 3 is less than k. So square root of k minus 3 is less than square root of k. And we divide again. 1 over root k is less than 1 over root k minus 3. This guy diverges, so this guy must as well. So since this series here is a divergent p-series, and 1 over root k is less than 1 over root k minus 3 for k greater than 4. We're not necessarily going to have to put that every time, though. We have that the series 1 over root k minus 3 diverges by DCT. So typical setup for answers here, we're going to have the series we're comparing to, what the comparison is, and so what our series does. So you can see here kind of when the direct comparison test will be most useful is when we can kind of easily establish the inequality. Right, so in this case, when there's kind of just sort of one extra bit tacked on. If this -1 wasn't here, we would have a really nice time because everything would be able to cancel out real nice, and we would have a nice p-series to work with. So if there's kind of just one extra bit tacked on, usually that means direct comparison test is going to be our guy. And so we'll go ahead and think about what would happen if this -1 wasn't here. So we won't even care about the index here. So what would happen if that -1 wasn't there? We'd have k cubed over 2k to the fourth. What would that be equal to? We'd get 1 over 2k. And we could take that 1/2 out and make it 1 over k. And so this would be kind of our idealized case. This is what we're going to eventually be comparing to. Just what happens if we take out that -1. So we'll go ahead and compare 2k to the fourth minus 1. We'll compare it to if that 1 wasn't there. It's less than 2k to the fourth. And so what we'll try to do from here is we'll go ahead and try to get this guy to appear in our inequality. So we'll go ahead and send both these denominators into the denominator. And so we end up with this setup here. And we'll multiply each side by k cubed. And notice that in this particular case, I started with 2k to the fourth minus 1 less than 2k to the fourth. We can readily establish that if we have the same number and we subtract 1, that it's less, right? So you can start there. So we've turned it into denominators. We multiplied by k cubed. On the right side, this is our a sub k. On the left side, we can cancel stuff out. And so here's our setup. We have the series that we know will diverge. This is harmonic. Less than the series we have in the problem. So 1 over 2k. This is equal to 1/2 sum of 1 over k. That is a divergent harmonic series. And so we can get our answer. Therefore, since 1/2 sum of 1 over k, oh, sorry, we want to put that in the same, we want to have this in our summation here. 1 over 2k is a divergent harmonic series, and 1 over 2k less than k cubed over 2k to the fourth minus 1. K cubed over 2k to the fourth minus 1 diverges by dct. All right, so that is using the direct comparison test then to establish that inequality and get our results. So it works very well when we just have kind of one extra number tacked on. So let's see another situation where it might be able to help us here. All right, so we have natural log of k over k to the third. So again, we want to figure out, is there some way that we can kind of make this nicer? Is there something that we would rather, if we could have anything we wanted, is there something that we wish that we could replace a part of this with that would make things cancel out nicely? It would be real nice if this natural log of k was just a k. Right, those would cancel. We get 1 over k squared. Convergent p-series. That'd be real nice. We know, based on growth rates, natural log of k is less than k, and this is going to be true for all natural numbers k, as long as we are greater than 1. Right? As soon as we hit k equals 2, then this is true. And hey, that's what we start with here. So typically speaking, we're going to have a good matchup between our index and what we need. So we'll go ahead and divide both sides by k cubed. And so when we do that, we get natural log of k over k cubed less than 1 over k squared, just like we wanted. So since the sum of 1 over k squared is a convergent p-series, and we show our inequality up here, it's acting as our roof for our series that we have here. That means that our sum, natural log of k over k cubed, converges by DCT, direct comparison test. Right? So another use for this is when we have natural logs that we would rather replace with k's. That's going to be actually a pretty consistent use case for us. So let's go ahead and look at the next one here. We can see, again, just having that 1 gone would be very nice for us. We'd have square root of n squared, and we know that we would end up with right, the harmonic series. Harmonic, there you go. So if that 1 was gone, we could do that. So let's go ahead and give it a shot. N squared plus 1 is certainly greater than n squared. So we take the square roots. When we do that, we get root n squared plus 1 is greater than n. Send these guys to their denominators. Send this guy down here, send this guy down here. We got 1 over n greater than 1 over root n squared plus 1. So divergent series, greater than our series. So this guy diverges, but the direction is wrong. We want the divergent series to be less than our series, so it kind of pushes it up. So we got to figure out something else. Looks like our issue here is we have that our guy is greater than n. So we got to figure out then what is something else that we can compare to that's maybe not just 1 over n. What if we multiply this by something? We can multiply this by maybe 1 over 2, right? That's not going to be equal anymore. This is 1 over 2n. Maybe there's some way that we can make that happen. This is still a divergent harmonic series. Let's kind of fit it in here and see what happens. So if we square it, that's 4n squared. So 4n squared is certainly greater than n squared plus 1. Okay, so right, this is n squared plus n squared plus n squared plus n squared. Right, and so from here we can go ahead and take our square root. Then move things into the denominator. And now, this is good enough. This is, instead of using the harmonic series, 1 over 2 times n, which is still harmonic. So since 1 over 2n is a divergent harmonic series, and we have established that it is less than our series, term by term, our series must diverge also. So we can see that sometimes our simplest sort of comparison doesn't quite work out, but we can see that there's usually going to be an easy fix, as long as we're willing to kind of puzzle it out. Right. Notice that these no longer really say that we have to use comparison test anymore. In fact, looking at this guy, I see that I have a bunch of stuff added in the bottom, which means that likely comparison test is going to be kind of difficult here. So what we want to try to do is, well, I'm looking and seeing a trinomial. Must try geometric or telescoping. Telescoping first. So let's try geometric or telescoping first. So, right, we obviously, very first, we do divergence test. This goes to 0, so we keep trying. So we'll go ahead and see if we can factor this trinomial. And I'll just use sigma to establish 1 to infinity. That's okay. So we'll factor. We get, let's see, k plus 2 and k plus 1. So we use partial fraction decomposition here. So 1 over, I'll switch the order too, just because I have a feeling this is going to be telescoping, right? So, a over k plus 1 plus b over k plus 2. So we clear our denominators. And then we have b times k plus 1. If k equals -1, then we've got, let's see, 1 equals a times 1 plus 0. So a equals 1. If k equals -2, then 1 equals 0 plus b times -1, so b equals -1. So we're looking at 1 over k plus 1 minus 1 over k plus 2. This is a telescoping series. So remember, for that, we set up our partial sums. We go ahead and add the first n terms together. So we plug in 1 for k first. So that gives us 1 plus 1 is 2, minus 1 plus 2 is 3, plus, plug in k equals 2, 1 over 3 minus 1 over 4, plus 1 over 4 minus, and so on, all the way up to, let's go ahead and put the dots back here. So n minus 1, we get n, and then n plus 1. Here we plug in n, we got n plus 1 minus whatever n plus 2. There we go, got it. So we go ahead and make our cancellations, cancels, 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 and so on, all the way down to we've got 1/2 minus 1 over n plus 2. All right, then we take the limit of those partial sums as n approaches infinity. So we get the limit as n tends to infinity of 1/2 minus 1 over n plus 2. This guy goes to 0, and so we get 1/2. So we get, therefore, the telescoping series (1 over k squared plus 3k plus 2 from k equals 1 to infinity equals 1/2. So that obviously converges if I've said what it's equal to, and so that's our answer. Great. So comparison test would not be very nice on this, simply because we have kind of extra stuff added in. It's not just a single constant. It could work, but in this case it was much easier to do telescoping series than trying to figure that out. All right, next one here. I see degrees are the same here, which likely means if we take the limit as k tends to infinity of our terms here, remember this is the divergence test. If we get 0, inconclusive. If we get anything other than that, diverges. So go ahead and multiply by 1 over k squared on both the top and the bottom. Get the limit as k tends to infinity. We got 3 plus 2 over k squared in the top. In the bottom, we got 1 plus 3 over k plus 2 over k squared. 0, 0, 0, we get 3. And so the series, therefore, the series, we're going to state what it is. The series k equals 1 to infinity 3k squared plus 2 over k squared plus 3k plus 2 diverges by the divergence test. So always be on the lookout for that. So the next one we'll move to is our second comparison test, the limit comparison test. So it says the direct comparison test should be tried if there is an obvious comparison series and the equality is easily established. And so we have, right, this is going to be a comparison to, right, the difference here is 1 in degree. Bottom degree is 1 bigger. This is a harmonic kind of deal that we're going to compare to. Right, in this case, the denominator is smaller, so this is bigger than the harmonic series because we have a subtraction. Now we have an addition. That's tough. The comparison doesn't work anymore, and that's when we have to get this kind of squirrely multiplying things. And we don't want to do that if we can avoid it. So rather than determining or manipulating the inequalities, we're going to use the limit comparison test. So here it is. Again, we'll have a series that's given by the problem and a series that is known. So we're going to have the problem series over our known series equal to L. If L is between 0 and infinity, then they both behave the same. So if L is a finite positive number, then both series will behave the same way. If L equals 0 and our known series converges, then our problem series does too. If L is infinity and our known series diverges, then our given series does too. Notice this could be a problem. If your series converges, but you get L is infinity, then you don't really know what your problem does. Something goofy has happened, something's gone wrong. Either something's gone wrong in your limit comparison test, or you should be using a different test. So we will very, very rarely run into those situations, if at all. So be careful. So we'll go ahead and take a look at this series here. We've got polynomials, right? Multi-term polynomials. That is the limit comparison test's greatest sort of asset to us, is when we have these multi-term polynomials. So what we want to do is we just want to look at the leading terms and think about that in a series. And we won't even look at the leading coefficient. So we'll just scribble out this 2. So we've got 1 over k squared. This is our comparison. The limit comparison test, that's our sort of best way for establishing what we're comparing to. We know that this is a convergent p-series. So we go ahead and look at L is going to be equal to the limit, as k tends to infinity, of, we put our problem series, our problem terms here. Oops, put that in the superscript also. There we go. Over the series we're comparing to. So 2k to the 6 minus k plus 5 over 1 over k squared. So we flip and multiply. Flip it, multiply it across the top here. We get k to the 6th minus 2k to the 4th plus 3k squared over 2k to the 6th minus k plus 5. So we'll go ahead and multiply the top and the bottom by 1 over k to the 6th. When we do that, we get limit as k tends to infinity. We got, let's see, 1 minus 2 over k squared plus 3 over k to the 4th over 2 minus, let's see, 1 over k to the 5th plus 5 over k to the 6th. 0, 0, 0, 0. We get 1/2. Which means that both series, the 1 over k squared that we compared to and our problem series, will behave the same. So since we have that L is between 0 and infinity, and 1 over k squared is a convergent p-series. So instead of writing what our inequality is equal to for direct comparison, we write what L is doing. And we have our convergent p-series. Our problem series, k to the 4th minus 2k squared plus 3 over 2k to the 6th minus k plus 5 must converge by limit comparison test, LCT. So it makes pretty quick work as long as we're comfortable enough with limits. So I think we can tell which of these comparison tests we kind of prefer. So we go ahead and revisit something that looks pretty similar to something that we've seen with our direct comparison test. Right, we would want to compare this to maybe 1 over n squared, but we see it's kind of gonna go in the wrong direction. So instead of trying to fiddle around with what weird thing can we kind of compare this to, let's go ahead and just compare to what we want if we didn't have that 4 there. So L will be equal to the limit as n tends to infinity. We've got our problem here over what we're comparing to. So we got the limit as n tends to infinity. We flip and multiply. We got n squared over n squared minus 4. Actually, let's go ahead and just use L'Hopital's rule for this one. This one should be pretty simple. The limit as n tends to infinity of 2n over 2n, that's 1. So since 0 less than L less than infinity, and our guy here is a convergent p-series, the problem here, 1 over n squared minus 4, converges by LCT. And now let's visit, again, our old friend here. This was the square root that caused us trouble before when we were doing the direct comparison test. Right, we were unable to compare it to our harmonic series. So now, using the limit comparison test, that shouldn't be a problem. So problem series on the top, comparison series on the bottom, flip, multiply. We got n over root n squared plus 1. The only issue now is we do have to figure out how to evaluate this limit. Let's go ahead and we can actually take our numerator and stick it underneath that root as well. And now a property of limit says that if there's a power on the entire argument of the limit, we can actually apply it to the limit on the other side. So apply on the outside of the limit instead. There we go. We can use L'Hopital's rule. So we get root limit as n tends to infinity of 2n over 2n. That's root 1, which is 1. So since 0 less than L less than infinity, and our 1 over n is a divergent harmonic series, our series, where we have 1 over root n squared plus 1, diverges by LCT. So it was able to make much quicker work than what our direct comparison test could have done for us there. All right, so now for these last couple problems, or this last problem rather, we'll just do kind of a grab bag. We'll kind of take a look and look at this with fresh eyes, figure out what tests we should do, what should happen with this guy. First off, we run the divergence test through our heads here. Definitely the denominator is going to grow faster than the numerator. We'll end up with 0. So we are good to continue using other tests. We have addition in our numerator. This isn't a polynomial, so there's no real point in keeping this together. So what we can do is we can go ahead and split this fraction up. And when we do that, we get 2 different fractions we're dealing with here. And we can actually split this into 2 different series. So we got k over k squared to the k plus another series, k equals 1 to infinity to the k over k squared to the k. We can simplify. K equals 1 to infinity. We can cancel out a little bit there. So we got k to the k. And then on our other side here, we've got 1 over k squared. It's easy enough to establish this guy is a convergent p-series. P equal to, so this is a convergent series. So let's say so. So this is a convergent p-series. For our other series here, we can kind of figure out what do we want to do. We can do perhaps a comparison. We can do a limit comparison maybe if we drop the k perhaps. This one looks like it would actually respond well to a ratio test. So we'll take the limit as k tends to infinity, 1 over k plus 1 to the k plus 1 over 1 over k to the k. So we get the limit as k tends to infinity. We've got k to the k over k plus 1 to the k plus 1. So we split up our k plus 1 stuff as best we can. It looks like there's not really much that can happen with this k plus 1 sitting there in the parentheses, but we can change the exponential into 2 to the k times 2, which cancels out some stuff here. So we get the limit as k tends to infinity of k over 2 times k plus 1. We use L'Hopital's. We got the limit as k tends to infinity of 1 over 2. So we get 1/2. And so we've got kind of two explanations, though, since we did have two different series. So since, well, this is less than 1. Since r is less than 1, we've got our series that we worked with here. Let's look at it as this was k over k squared 2 to the k. Converges by ratio test. We can say furthermore. We've got our other series here, 2 to the k over 2 to the k times k squared is a convergent p-series. That was a terrible way to write convergent. Convergent p-series with p equal to 2. So our series that we started with then, k plus 2 to the k over k squared 2 to the k converges. For what reason? As a sum of two convergent series. That's going to be what we want. So we have a lot of different tests, and many of them are very situational. So we kind of have, again, a summary here at the bottom. Reasonable course of action when testing a series of positive terms for convergence. All positive terms. So we're going to change that up next section. But first off, do divergence test in your head. Second, look for the easy way out. Is it geometric or telescoping? After that, next easiest thing is a p-series. And then usually, if we can integrate it, we're going to have to. So I would really probably save this for last. Go ahead and check everything else first. If the k term involves k factorial, k to the k, or a to the k, try ratio test. If k is only in an exponent, try the root test. If the kth term is a rational function of k, right, so we have polynomials, something like that, or a root of a rational function, so polynomials with roots on them, do a comparison test. And we're going to compare to stuff from 2 and 3. Then I would say after that, yeah, if you have to, try the integral test. we know that's long and arduous. All right, so these are all of our tests then for positive terms for our series. So next time we'll go ahead and look at what happens if we start throwing negatives in there as well.